Hello and welcome to lecture 36 of the course Computational Complexity. Right. In the previous lecture we saw that every language has a circuit of size 2 power n and order 2 power n, and then we saw that there is a better bound order 2 power n divided by n. Right. And at that point I mentioned that this is rather tight, and we will see the proof why it is tight. So the reason is there is a theorem by Shannon that says that there are languages that 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 require at least 2 power n divided by n size circuits, right? So the formal statement that I have written here is that there are languages that require that cannot be computed in circuits of size 2 power n divided by 10 times n. So the denominator has an extra 10. So this 10 is somewhat arbitrary, right? We'll see why, right? And we'll prove this, and then we will lead on to something at hierarchy theorem for circuits. So we saw time hierarchy and space hierarchy, right? So we saw Turing machines, or if f is a function, g is another function in terms, right? And if f is sufficiently smaller than g, then there is a language that cannot be computed in f but can be computed in g time. Similarly, when f is sufficiently smaller than g, then there is a language that cannot be computed in f space but can be computed in g space, right? This is what we saw. In exactly the same spirit, we will see the circuit hierarchy theorem, where we will say that when f and g are appropriately chosen functions, so that f is rather small and g is somewhat smaller as compared to g, and also satisfying some other bounds. So we'll see why this is important. In that case, there is a language that can be computed by g but cannot be computed by f, right? So this is what we will do in this lecture. So first we will see Shannon's theorem, why there are languages such that cannot be computed in 2 power n divided by 10 n size circuits, right? And this is an extremely simple kind of argument. All he does is sum counting, right? So let us see first, as a first step, let's see how many circuits are there of a certain size, and then we will see how many functions are there of a certain number, of a certain for a certain n, and then we'll say that if the size is small enough, or sorry, size is small enough, then that size is not enough to even enumerate all the functions, right? So unless size is big, you cannot possibly compute all the functions. So let us see the full proof. So first, let us see how many circuits are there of a certain size, right? So to make it simple, we will just restrict ourselves to the De Morgan basis: AND gate, OR gate, and NOT gates, right? So it is easier to see to bound the number of descriptions of a certain circuit, right? And then use that to let's say if we say that all the descriptions are of size 10 or 100 bits long, then we know that there cannot be more than 2 power 100 circuits, right? That's what we will do. So how do we describe a circuit, right? For each gate in the circuit, we need to specify two things. One is what type gate it is, right? So there is one of AND gate, OR gate, or NOT gate, right? These are the three things, and this requires, let's say, constant bits, right? Maybe 2 bits are enough, right? There are 3 possibilities, so 2 bits are enough. And for a given gate, let's say for a specific gate, say gate I, which are the inputs, or where are the inputs coming from? sorry, I apologize for my handwriting. Where are the inputs coming from? I think I may need a bit more space. Yeah, that's enough. So let's see how this works. So given a gate, we already said we will restrict to De Morgan basis, and in fact the theorem statement says, no, theorem statement doesn't specify, but we will restrict ourselves to AND gate or gate of fan 2. Okay. So for so we need to specify left child, where the left child comes from, and we need to specify where the right child comes from, right? So if it's an AND gate, it has a left child and right child. We need to specify where these come from. So we have already said that we are talking about circuits of a certain size S, right? So there are S gates. So it could be from any of these S gates. There are also these N inputs. So it could be from these N inputs also. So the left child could be one of the N plus S possibilities, and right child also could be one of these N plus S possibilities. So in order to describe this, we need log N plus S bits to describe the left child as well as the right child, because there are N plus S possible potential places from where you can choose the input, right? So now to specify the circuit, right, or to completely specify the gate, we require, so first of all, let's say 3 bits, constant number of bits, let's say constant, or maybe we can say 3 bits, right, or maybe it's 2 is enough, let's say 2 bits to specify the gate type, right, and plus this 2 log N plus S to specify the inputs. Now 2 log N plus S, so one way to bound N, so the size of the circuit will at least be the length. So N is upper bounded by the size. So you could write it as 2 log 2 plus 2 log 2s, and this 2s can be, this 2 can be again split into this is equal to 2 plus again 2 plus 2 log s, right? Log 2 is 1 and 2 log 2 is 2. So but now we have a constant 4 outside, but then 4 plus 2 log s we could just upper bound it by 3 log s. This is to specify one gate, right? To specify all the gates, so to specify all gates, to specify S gates, we need 3s log s bits, right? And once we have that, the description of the circuit is 3s log s, and how many such circuits can be there? It is just 2 power that, right? So as I said already, so it is 2 power 3s log s circuits are there of size s, right? Now how many functions are there of a from 0 1 power n to 0 1? So how many input combinations are there? The number of input combinations are, there are 2 power n input combinations, and for each of these input combinations it could be one or two possible choices, 0 or 1. So this is, the answer is 2 power n, right? So this is the answer, this is the number of functions. So for a certain sized circuit, there are only 2 power 3s log s circuits of a certain size s, but for a given n there are 2 power n functions, right? So what we have to do is choose S in such a way that 3s log S is smaller than 2 or so we need to choose S. We will choose S so that 3s log S will be less than 2 power n, and this is the key thing. Sorry, this is the key thing. This is going to be the key thing. 3s log S less than or equal to or strictly less than 2 power n, which means that for that size there are only this many circuits, so it cannot possibly compute all the functions of from 0 1 power n to 0 1, right. So if you choose S to be 2 power n divided by 10 n, right, then if you compute 3s log S, it just happens to be 3 times 2 power n divided by 10 n times log of this, but log of this can be upper bounded by log of 2 power n, so it is just n. So the n in the 2 power n and n in the 10 n cancels, so you get something like 2 power n divided by, so one step if I want to add, it is 3 times 2 power n divided by 10 n times log 2 power n divided by 10 n. This is less than or equal to, so log 2 power n I replace it by n, so 3 times 2 power n divided by 10, and this is strictly less than 2 power n divided by 3, right. Again, this I think this is a straightforward calculation, but I am erasing it. So, but anyway, the point is that 2 power n divided by 3, right, this exponent is actually less than this exponent 2 power n. So, and in fact 2 power n divided by 3 is like 1/3 of 2 power n, but once they are in the exponent of 2, 2 power n divided by 3 is much smaller than 2 power n, right. Right. So this is much smaller. So number of circuits of this size, 2 power n divided by 10 n, is way smaller than the number of functions, which means there is at least some function that is not captured by a circuit of this size. It cannot be the case that all of the functions are captured, because each function requires a separate circuit, right. So that completes the proof that there are functions that require more than 2 power n divided by 10 n sized circuits. So that is the proof, right. However, there is one interesting point here, or two interesting points rather. The first thing is that 2 power 2n is way bigger than 2 power 2n divided by 3, right. So it is much bigger. So just to compare, if you want to take 2 power 3 is 8 and 2 power 9 is 512, right. So even at the small scale it is so big. Or 2 power 10 is 1024 and 2 power 30 will be, so 1024 is like 1000, 2 power 30 will be like a billion, 10 power 9, right. So it's you can see how big these are, which means the number of functions are way more than the number of circuits, which means if you pick a function at random, right. So by random I mean you could do any reasonable process. One possibility is to look at all the inputs and flip them 0 1 based on a random choice, right. If you pick a function at random, it is very unlikely that it will have a small circuit. By small I mean by this size 3s log s or 2 power n, sorry, this size 2 power n divided by 10, right? Because the number of circuits of this size is very small. So the number of functions that have a circuit of this size will also be small. So a random function that you choose is going to be very likely to require a circuit of a bigger size, right. However, So you may think that okay, most of the function, if you pick a random function, it will require a lot. It will require more size than 2 power n divided by 10n. But this is true, but still there is this problem. Most of the natural functions that we can think of actually require only a small circuit, smaller than this 2 power n divided by 10n. In fact, people have tried to construct circuits that functions that require big circuits, and people have been incredibly unsuccessful in this. So again, this proof is some kind of not an explicit proof, right? It just says, it just counts the number of functions, number of circuits, and produces, and says that there has to be a function that requires a large circuit, but it doesn't tell you which function it is. And people have tried to compute which function it is, but without much success. In fact, forget 2 power n sized circuit or 2 power n divided by 10. Even n squared, even for n squared, we don't know which function requires an n squared size circuit. In fact, the best known explicit function, right? Let's say for if you just allow, let's say, AND gate, OR gate, and NOT gate, right? Of fan 2 is of size roughly 5n, or requires size 5n. So that is just 5 times n. So forget exponential size. We don't even know quadratic size. We don't even know linear beyond 5n. Let's say 10n. We don't have a function that requires 10n size, right? So we have this interesting situation where almost all functions are hard to compute, but if I ask you produce one function that is hard to compute, people haven't been able to do that, right? Okay, so that is the Shannon's theorem, and from there we will go to this hierarchy theorem, right? So what I've stated here is, if 25 times n times fn is strictly less than gn, then there is a function, right? So fn and gn are we are talking about size. They are size bounds. Okay, they are not the functions themselves. They are functions that denote the size of the circuit, right? In that case, there is a function that cannot be computed in fn size but can be computed in gn size. That is the theorem. So it's a hierarchy theorem, but interestingly, both the hierarchy theorems that we saw so far, time hierarchy as well as space hierarchy, use diagonalization. Whereas it is not so easy to, or it's not clear how you would apply diagonalization to the circuits, because in the case of time hierarchy, space hierarchy, we could list down Turing machines and so on. But here we cannot list down all the circuits, because a circuit family itself has infinitely many circuits. So it's not clear how to apply diagonalization. So what we will do is, we will not, so whatever the ingredients that we required, we have already shown. We will just use those ingredients, right? So we saw that there is, every language has an order 2 power n size circuit, or rather 5 by 2 times 2 power n size circuit. I am referring to this result, right? And we also saw that there are languages that require more size than 2 power n divided by 10n size circuits, right? So we just use these will be our ingredients. Okay, and why do we have this upper and lower bound? Which so we certainly didn't have an upper bound in the case of time hierarchy or space hierarchy. This is because we need an upper bound, because we know that all functions are computable in, or all functions have a 5 by 2 times 2 power n size circuit. So if we did not have an upper bound, and if you took something like 100 times 2 power n, gn to be 100 times 2 power n, and fn to be, you divide 25 divided by n, so you got something like 4 2 power n divided by n, right? And this happens to be bigger than 5 by 2 times 2 power n. So both g and f, even f will be enough to uh, decide all the functions, right? So, or the languages, right? So that is why it is important to have an upper bound here. G should be sufficiently smaller than the number at by which you can compute all the functions, right? If G is much bigger than that, then even F will be bigger than that, right? So we need an upper bound here, and lower bound, it's N is like a trivial lower bound. Okay, what have we seen so far? We have seen that there are functions that cannot be computed in 2 power L divided by 10L size, right? That cannot be computed in 2 power L divided by 10L size. So, and every function can be computed in 5 by 2 divided by 2 power 5 by 2 multiplied by 2 power L size. So basically, it is just this. This is the factor 5 by 2 in the numerator, 10 in the denominator. If you multiply 10 with 5 by 2, you get 25, and that 25 is what we have in the statement here. And this L in the denominator shows up as N in the N in the numerator with Fn. So that's how you get the 25N. Okay. So we choose an L such that Fn will be roughly 2L divided by 10, 2 power L divided by 10L. Okay, so this is 2 power L. So Fn will be roughly 2 power L divided by 10L. That is all that we do. So G will be, so because of this condition, G will have to be at least 5 by 2 times 2 power L. Right. So why is that? So Gn is at least 25N times Fn, and we will choose N in such a way that N will be bigger than N, right? So this means it is at least 25L 2 power L divided by 10L. So L cancels, so which is equal to 25 divided by 10 is 5 by 2 times 2 power L. So Gn is bigger than 2 power L. So which means that Gn will be able to is enough to compute all functions from 01 power L to 01. 01 G is sufficiently big to capture all functions, and F is certainly, we know that there are many functions from 01 power L to 01 that cannot be computed in F, right? F size. So now choose such a function H that is computable, or that is decidable in using a circuit of size that is not decidable with a circuit family or circuit family of size 2 power L divided by L, and this H will automatically be decidable in G, right? So this H, maybe I'll write that, H will also be in size G of N. Right, because of what we said here above. So now the only thing that so we defined size H to be so we have chosen H to be from 01 power L to 01. Now all we need to do is to lift it to the 01 power N domain. So we'll call it H prime, which is from 01 power N. So how do we do that? All we need to do is define H prime of X to be, so H prime is acts on an n bit input, and we define it to be H computed on the first L bits of X, first L bits, right? So H prime is nothing but you look at the first L bits. So this is 0, this is 1 to n, or 0 to n. So let's say this is L. So H of this quantity is the H prime of the entire string. So now what happens is that H prime is not, we don't have a circuit of size Fn for H prime, but we have a circuit of size Gn. So that's all that we need, or that's all that we wanted to show. In fact, I'll just I'll just make some space here. Sorry. Sorry, my tablet is taking a bit of time. Okay. In fact, if we used so this for this proof, we used that every function can be computed in size 5 by 2 multiplied by 2 power n, right, which is what we showed in the previous lecture, right, this bound. But however, I said that there is a Lyapunov's bound which says that every function has a size 2 power n divided by n size circuit. So if we use that, then we could get a statement. If we use Lyapunov instead of the other bound, we could get a tighter result. We could get a better result, not tighter, better result. So n can be less than, so there the difference will only be a factor 10, right, because this will be 2 power L divided by 10L, the functions that cannot be computed in size, and this will be just 2 power L divided by L. So it will just be a factor of 10 difference. So strictly less than Gn and strictly less than 2 power n divided by n, right. So if you use we will get a better result actually. So, but then that's fine. So anyway, the point is that if you have more bigger size circuits, you could compute more functions, and that is the main point that I want to convey here, right. So what we saw in this lecture was basically two results. One was the Shannon's theorem, which says that there are languages which require 2 power n divided by 10n size circuits, or even more than that. So this together with the Lyapunov's theorem shows an almost tight situation. So every language requires every language can be computed by 2 power n divided by n size circuit, but 2 power n divided by 10 size circuit is not quite enough, right. So it's only a constant factor of, and which was just by a counting argument, Shannon's theorem. Then you just counted the number of functions and we just counted the number of circuits, and we saw that when the size was this 2 power n divided by 10n, then we could not, the number of circuits itself is smaller than the number of functions. And we mentioned the randomly chosen function so that in fact the number of functions that cannot be computed in this size are the majority, or an overwhelming majority. So most of the functions cannot be computed in this size, but it has been an embarrassing situation. Most of the functions, almost all of the functions that we know can be computed in simple, easy, small size circuits, and we do not know of an explicit function that requires this much size, and far from it, in fact, right. And then we saw the hierarchy theorem, which used both the Lyapunov and the Shannon's theorems. And yes, I think with that we'll conclude this lecture. Thank you.